Okay, so now we've done particle extraction and it is time for 2D classification. Keep in mind that this is a step that has a really big effect on your final map and the quality of your map. And there are a lot of options to optimize classification. And for this video, just because its intended purpose is to get you off the ground running, I am not going to go into in-depth detail about each option, but I will talk about the high points, and I will link other videos that I think explain things like the option to ignore CTFs until first peak, or doing 2D classification without image alignment later on, and you'll see those tiles here. So just to get started, our input for 2D classification could be the star file or the particle stack from our extraction. It could be from the selection of other 2D classes. It could be from the output of a 3D classification or a 3D refinement. There are a lot of options. So for us, because we haven't generated a model or anything like that yet, we're just going to use our extracted particles. So do that here, and we will leave all of our other settings as default until we get to the optimization tab. So the first thing we're going to do is select a number of classes. And if you look through the RELION tutorial, Shoreshairs recommends for each particle something like, or for each 200 for every 200 particles, you use another class, up to I believe he likes the number 200 classes. And because we only have 24 micrographs here, I don't think that 200 classes is quite necessary. And I believe from the output in our extract file, we have about 10,000 classes. So 10,000 divided by 200 would be something like 50. So we'll do that to begin with. Okay. So we go 50. We'll leave our regularization parameter at 2. I'll link another video to that because I think that's worth discussing in detail. And then the number of iterations we'll leave at 25. Sometimes it's worth doing much more than 25 iterations. And then we have the option to use fast subsets for large data sets. And this is worthwhile when you're processing hundreds of thousands or millions of particles. And what that does is use a smaller number of particles initially to create initial class averages, and then it builds on that until running a full data set 2D classification later on. And they have a really good explanation of that here. If you press the little question mark, it explains exactly how that works. And then now we have our mask diameter, and we want that to be slightly larger than the particle itself, so slightly larger than the max diameter. And this is something that I would like to go into a little bit of detail here because it's something you need to understand from the get-go. So let me start my slide. I pulled up our extracted particle from the previous micrograph, and it looks like this. And I blew it up because I wanted to kind of demonstrate how much noise contributes to each one of these images. We can see our particle here, and then the noise on the outside of that could contribute to low resolution class averages. So the way that we combat that, or the way we combat the influence of noise on the alignment of our particles, is by applying a mask. So I've done that here, represented by this blue circle, and what RELION will do is actually exclude any information outside of this blue circle and only focus on information within it to align our particles. Now, another instance in which you might want to use a mask is given here, where we have a protein that has two flexible ends. Let's imagine that it's like a homodimer or something like that, and it's split down the middle. and it has, you know, a floppy domain over here and a floppy domain over here, and the alignment of the center is represented by this arrow. Now what we might have is, because these regions are flexible, one region being perfectly in a line and then another domain being slightly off. And what we'll see is that without a mask, the alignment of those two might result in something like this, where the offset of this domain, let's say on the left, might influence the center to be slightly off later on, right? And I think the best way to tackle this would be to apply a mask to the center and then later go on and 3D classify these regions to find the variability within them. And what you would do in this case is apply a mask to only focus on the center and not the whole particle. So there are two instances where this just brings up two instances where you might apply a mask to the whole particle, or apply a mask within the particle to mask out any variable regions that you want to classify with 3D variability later on. Okay, so and ideally we would apply that mask and come up with something like this, where we have a perfectly aligned center particle and we don't see the external regions. Okay, so if we exit from there, we can actually move on to our 2D classification again. And we earlier, through manual picking, decided that our maximum diameter of these particles was approximately 200. So we'll go with a mask diameter of something like 220, just to give a little extra wiggle room. For sampling, initially we'll leave everything default, and then in my particular machine we can increase the number of pulled particles to 64. This will vary depending on the machine you're using, and they give an explanation of how many particles you could use over here, and it's dependent on the number of CPUs and GPUs you're using. So we want to use GPU acceleration for this, and again, my machine has 4 GPUs and 12 CPUs allocated per GPU. And then for my job alias, I like to give something akin to this. My input classes, so extract 8, and then my mask size is 220, and I am using 50 classes. And later on, that's helpful if you vary the number of classes or mask size or something like that. So now we'll run that, and in the next video I will show you how to examine your 2D classes. It looks like we've had some abort, but we'll just pretend it's running. In the next video though, we'll examine our 2D classes and talk about how to pick those with the subset selection tool.